Question 7 from Paper 1 of the 2022 Higher Physics exam from the SQA. A spacecraft passes the Earth at a speed of 0.4 c. A light in the spacecraft pulses on and off. A passenger on the spacecraft measures the time between the pulses as 2.5 seconds, and an observer on Earth measures the time between the pulses as, and you're given your 5 choices. Here's a picture of the situation. We have the Earth and we have the spacecraft whizzing past the Earth at 0.4 c. That's 0.4 times the speed of light, 4/10 the speed of light. Now, when you're on the Earth, you will measure a time called t prime, and that's called the measured time. When you're inside the spacecraft, you will measure what we call the proper time. And the two of these times are related by the following equation. T prime, the measured time by the observer on the Earth, is equal to the proper time as measured in the spacecraft divided by the square root of 1 minus v upon c all squared. So we're after t prime. So that's the first thing we put down. We have to find what t prime is. That's the questions we're looking for. T, we know, is the proper time. That's the time measured in the spacecraft, and it's going to be 2.5 seconds between these pulses. We know the speed of the actual spaceship is going to be 4/10 the speed of light, 0.4 c. So all we have to do is put those into equation, and we have t prime is equal to the t, which was the time measured in a spacecraft, 2.5 seconds, divided by the square root, and because we've written the speed of the spacecraft relative to the Earth at 0.4 c, we can have the following: 1 minus, and it's going to be 0.4 c all squared divided by, and it's going to be c squared. You can see the two c squareds cancel out, and you're going to be left with 2.5 divided by the square root of 1 minus 0.4 all squared. And we do that in our calculator, we end up with a time of 2.73 seconds. Now we can put it to two significant figures, and that will give us an answer of 2.7, which is going to be answer C. Question 8 from Paper 1 of the 2022 Higher Physics examination from the SQA. A student makes the following statements about the expanding universe. Statement 1. The evidence supporting the existence of dark matter comes from estimations of the mass of galaxies. And statement 2. The evidence supporting the existence of dark energy comes from the accelerating rate of the expansion of the universe. And finally, statement 3. The peak wavelength of radiation emitted by hotter stars is longer than that for cooler stars. And we're asked to find out which of the following statements is or are correct. Well, let's look at the first statement about the evidence supporting the existence of dark matter and where it came from. If we apply the normal Newtonian gravitation to a particular galaxy with a large mass at its centre, probably a black hole, we should get this. The distance from the centre of the galaxy, the star's velocity should be a lot less than the stars near the centre of the galaxy, and that follows on from Newton's law of gravitation. But what really happened was, when Vera Rubins looked at the rotational velocity of the stars round about the galaxy, she found not this Newtonian gravitational curve, but this one here. She found out that the star's velocity remained constant over the distance from near the centre to the outer rim. Now, the only way to describe this is to say that there must be some sort of kind of hidden mass there, which is going to give rise to this extra force, which is going to make the stars go faster in the outside of the galaxy. So this led to the belief that we've got to add in extra mass, and this extra mass cannot be seen because the visible stars from that galaxy, when they were toted up for their mass, fell far short of what was needed to give this graph here, which means that the stars in the outer rim of the galaxy move just as fast as the stars near the inside of the galaxy. The only way to actually describe that, one theory was that there must be some missing mass, and that mass cannot be seen, and therefore that was called dark matter. So that's the answer to question 1, which rises from the study of the velocity of rotation of the stars round the galaxy. So for statement 1 is correct because the evidence supporting the existence of dark matter does come from the estimations of the mass of the galaxies, which came from the measurement of the speed of the stars in different parts of the galaxy. Now, statement 2, the evidence supporting the existence of dark energy comes from the accelerating rate of expansion of the universe. Well, that is correct as well because the universe is expanding and it seems to be accelerating as it expands. And the only way to describe it is there must be some sort of kind of hidden energy doing that acceleration, that expansion of the galaxy. So statement 2 is correct, and that's what we call this hidden energy. We call it dark energy. Now, statement 3 is all about the case of the black body radiation from a star. It says the peak wavelength of radiation emitted by hot stars is longer than that for cooler stars. Well, let's take a look at a cooler star, and we can see that its wavelength, the peak wavelength there, is 0.547 micrometers. Now, if we compare that with a hotter star, you can see that the peak has got larger, and the wavelength, the peak wavelength, has actually got smaller. So the peak wavelength from the hotter stars moved towards the shorter wavelengths and not the longer ones. So for this question, it seems to be that the answer is going to be statement 1 is true, and statement 2 is true, with statement 3 being false. So we have 1 and 2, and that's going to be answer D. And thanks to the people who pointed it out to me in the previous question when I was concentrating too much on the velocity of the stars. Thanks for that. Question 9 from the 2022 Paper 1 from the SQA. A police car is travelling at a constant speed of 31 metres per second towards a stationary observer. The siren on the car emits a sound of frequency 820 Hz. The speed of sound in the air is 340 metres per second. So the frequency of the sound heard by the observer, and you're given the 5 usual choices. Well, you go straight to your data book because you know that this is going to be a Doppler effect equation, and a big decision to know which one of the plus or minus on the denominator we're going to use. And the quick rule is when something is approaching you, as this car is travelling towards the station observer, we think of the distance becoming less, so we use the subtraction one, that's the minus one. So the equation we're going to use for this particular setup is going to be the frequency heard by the observer is equal to the frequency of the source multiplied by the speed of sound divided by the speed of sound divided by the speed of the source. So what we have to do is plug these equations into values into the equation, and we get the frequency of the source is going to be 820 Hz, and we're going to multiply that by the speed of sound 340 divided by 340, and this time it's the minus the speed of the source, which is going to be 31 meters per second. So if we do that on our calculator, we end up with the following. We end up with 902 Hertz. We're going to get a higher frequency, and that's what we really hear. And the answer to that will be letter E.